Hello, AP Physics C. Today we're going to talk about current density. Current density is current per unit area. So it measures how much current is going through any particular spot in there, but not the amount of charge passing through, but the amount of charge that's passing through per unit area. So when we calculate current density by dividing out the current that's running through any part of a wire or any part of a circuit, and dividing it by the cross-sectional area that you're going through. Let's do an example using this equation. And in this example, we have a wire of radius 0.001 meters, or a millimeter wide wire, and it has a current going through it of 0.02 amps. And what we want to find out is what the current density in this wire is. Well, we need current, which we have, and we need area. So our first step here is going to be to calculate what the actual area of the wire is. And so to calculate that area, we have to multiply, or find the area of the wire. It's a circular wire with a radius, so it's pi r squared. So pi times the radius squared gives us a area of 3.14 times 10 to the negative 6 meters squared. And once we have that area, then we can put it into our current density equation, which is current divided by area. And here we have our current divided by area, 0.02 divided by 3.14 times 10 to the negative 6 meters squared. That gives us 6,400 amps per meter squared. When we talk about current density, it's just another way of looking at current. It's not the typical way. We typically just look at current, but it does help us to understand what's happening. The other thing that we want to take a look at within this standard is electron drift. So we want to sort of understand how electrons move through conductors. When we have an electric field, right, that's pushing on charges, because charges move due to electric fields, when you apply that to a conductor, electrons are going to start moving within the conductor. But the way that the electrons move is not a linear methodology. It's not a constant motion, right? This is because the atomic structure of the circuit itself, or the conductors, have all these different charged particles, electrons and protons, nuclei that all have different charges and different forces that are acting on the electrons. So the electrons themselves sort of move rather randomly. This kind of ties into that current density idea in the sense that when an electron goes into a conductor, it doesn't just make its way path through it. It starts kind of displacing other electrons. It itself kind of moves rather randomly through it as it kind of picks its way. And that's what we find. The drift velocity of anything going through an electron or a conductor sort of depends on this atomic structure. So if we want to figure out how quickly electrons move through something, we can look at current density. That's good, but trying to understand this drift velocity is something we need another methodology too, and it's going to have to take into account the actual atomic structure of the conductor, which is entailed within its resistivity. So we've talked about resistivity last year, which is an inherent resistance to the move of charge through any material, and all conductors have that. So if we're trying to figure out current density within the concept of resistivity and within the context of this electron drift velocity, we could sort of kind of tie a couple of these concepts together. So we have drift velocity is equal to this formula here, and it's n, e, and then vd. So n is the number of elementary charge per unit volume, and this is going to, again, depend on the material you have. So it's e per cubic meter. Just how many charges do you have in some volume? We have e itself, which is just the elementary charge. And then we have this drift velocity. So our current density, we can figure that out. And then it's pretty easy to go between current density and actual current, because current density is just current per unit area. So if you multiply your current density by area, you're going to get your current itself. And this is a way of looking at it at the atomic structure, where we have elementary charges in a certain volume. We have the charge of the elementary charge. We have how quickly electrons themselves are drifting through, and the area itself. If we want to relate this concept to electron or electric fields, we could start looking at electric fields and current densities together, because the current density in a material depends on this resistivity, because the resistivity is that inherent resistance to moving those charges. So if we have that concept, we could look at electric fields themselves are equal to the resistivity, right, times electron, or times current density.